Hello, everybody. My name is Associate Professor Diane Kenwright, and I'm an anatomic pathologist who works for Wellington SCL and is head of department for the University of Otago, Wellington, Department of Pathology and Molecular Medicine. In my daily work, I see a lot of DNA mismatch repair immunohistochemistry, both in endometrial samples and in GI samples. And today I'm going to talk to you about the underlying scientific basis of DNA mismatch repair staining and also some tips and tricks for when it doesn't quite go as expected. Before we begin making sense of mismatch repair, I'm going to show you a video of what's actually happening inside cells as they replicate. Wait till the end and you'll see it all happening in real time. You'll be amazed at how fast those biochemical mechanisms stack that DNA.
DNA replication is carried out by a molecular machine called the replisome that pulls apart the double helix and makes an exact copy of each strand. In this visualization, we're going to examine the mechanism for copying DNA. The enzyme DNA polymerase synthesizes DNA molecules, using the original molecule as a template for the production of a complementary strand. The genetic code in the template strand is paired to free-floating bases, matching cytosine to guanine and adenine to thymine. DNA polymerase creates an exact copy of your DNA code, making less than one mistake in a billion bases.
Normally in DNA replication, the C's line up with the G's and the A's line up with the T's, but sometimes, as here, there is a mistake, a mismatch, and so it needs to be fixed. We're going to look at the processes that lead to this mistake being fixed. There are 4 DNA mismatch repair proteins. They come in 2 pairs. MLH1 and PMS2 is one pair, and MSH2 and MSH6 is another pair. The role of DNA mismatch repair proteins is to detect a mismatch and then label it. In a final step, they make the initial incision for correcting the mismatch. The next thing that happens is an enzyme, exonuclease, comes along and removes the damaged section. And then a further enzyme comes along and repairs it again. Thus, when mistakes happen, they can be fixed. Now the G is lined up with a C. What is microsatellite instability? Microsatellites are repeat sequences of DNA. As you can see in green here, AC, 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 going on for quite a while. If DNA mismatch repair is broken, then mistakes accumulate in these long repeating segments that aren't easily fixed. Here we can see that there is a point mutation, and here we can see there's been a point deletion, so there's been a frame shift. We can use PCR to detect the difference in these repeat regions. If there are lots of mistakes, this indicates that the microsatellite instability is high, and we call it MSIH. So MSIH means that DNA mismatch repair isn't working. What causes DNA mismatch repair to stop working? To understand this, you need to know that as well as the enzymes, there is an on-off switch. It's particularly important for switching MLH1 on and off. You can see here that this switch, represented by a computer type on-off switch, is on, so the whole system is working. MLH1 deficiency in cancer has two causes. The first one is to do with the MLH1 promoter, the on-off switch. The MLH1 promoter can become hypermethylated and be turned to off. This happens in about 15% of sporadic colorectal carcinomas. The other way that MLH1 can be lost is by an MLH1 germline mutation. Here we can see the promoter remains on, but there is a mutation which has permanently switched off MLH1. This is what normal MLH1 immunohistochemistry staining looks like. This is a colorectal carcinoma, and you can see that there's nice strong nuclear staining in all the tumor cells, with a bit of staining also in the background lymphocytes in the fronds here. This is what happens when there is MLH1 loss. You can see here that the lymphocytes and stromal cells are still staining positively, but all the nuclei in the tumor here have no staining at all. They're just blue and negative. Now, there is one important trick, and that is sometimes when MLH1 is mutated, it's not entirely lost. It has this weird dotty pattern here. So this is also an aberrant staining pattern, and it happens particularly with the M1 clone. Every time MLH1 is lost, PMS2 is also lost. You can see here that the tumor cells are negative, but the stromal cells remain positive. So why do we test BRAF in MLH1 deficient colorectal carcinoma? This is BRAF. You might recognize BRAF from another context. BRAF is looking angry because BRAF is mutated. The job of BRAF is to cause methylation, in particular these little things called CpG islands, which happen to be present on the MLH1 promoter. So the BRAF causes the MLH1 promoter to become methylated, which then switches off MLH1. If we detect the BRAF V600 protein with IHC, we know that the BRAF is mutated at the V600 point, and we also know that MLH1 is lost because of promoter methylation, and this only happens in sporadic cancers. What if PMS2 is mutated? So here we have the happy normal situation with the MLH1 promoter on and the two MLH1 PMS2 big sister, little sister enzymes working. If PMS2 is mutated, then we get loss of staining in PMS2. Here we have the other immunohistochemical stains, normally staining in the nuclei, and PMS2 here is lost, or maybe very, very weak. If there's mutation of MSH2, the big sister, by a germline mutation, then we get loss of MSH2 and MSH6. But MLH1 and PMS2 are preserved. So if the big sister is lost, like MSH2 or MLH1, it wipes out the little sister as well. What happens if MSH6 is mutated? In that case, we just lose MSH6. So if the little sister is lost, just that staining is lost. The MSH2 MLH1 and PMS2 remain intact. So why is this? Why, if we lose, the big sisters are both lost, but if we lose the little sisters, only one is lost? The answer is that the big sisters MLH1 and MSH2 can pair with any of the other mismatch repair proteins, and there are 7, and continue to be expressed even when their usual partner is lost. Hello, PMS1. Your sister PMS2 is mutated. I want to pair so I can express myself. And off she goes, pairing with PMS1 instead. In endometrial cancer, BRAF is not an important mechanism for causing methylation. MLH1 promoter methylation occurs by a different mechanism. BRAF is innocent in this case. The person who's at fault is in fact DNA methyltransferase, which is hyperactive. So while MLH1 is switched off by its promoter, looking for a BRAF mutation won't help us in finding whether or not it is the cause, because they're innocent. So what we have to do is look directly for the amount of methylation present in that particular genome. And this is done by molecular methods. Now we're going to move on to a different section. We're going to ask, is the IHC okay? What do you think about this? This is an endometrium, and the glands are staining positively, as is the surface, and there's a few positive cells in the background stroma. Is the IHC okay? Yes, this IHC is okay. We're getting a really good, strong positive and clear negative staining. How about this? Is this IHC okay? We can see it's a bit weaker here in the glands. There is still some positive nuclei in the background, and this tumor here is staining positively. Is this IHC okay? Yes, this IHC is okay too. How about this IHC? It's much stronger. We're getting very strong staining in the glands, in the stroma, and also in the smooth muscle. This IHC is a bit strong. It is staying rather too strong, and we might be worried that this is overstaining and we wouldn't be able to detect any subtle loss. Sometimes we see absent DNA mismatch repair staining in the tumor and internal controls for all 4 stains. It happens in big resection specimens. And it's due to tumor autolysis, either inside the patient before the specimen's been removed or while it's sitting on the bench. So sometimes cutting them open doesn't actually help. This is what it looks like. Is this okay? No, it's not okay. It's a waste of time, money, and we can't get any results from this. So, top tip number 1 for staining mismatch repair is to always stain the biopsy or curettings if available. They're well preserved. As well as not being autolytic, they also don't show neoadjuvant loss. So colon cancers that have had neoadjuvant therapy, particularly chemoradiotherapy, causes the MSH6 to be lost. What about if there's patchy mismatch repair protein staining in the tumor and all the internal controls for all stains? Again, this mainly happens in the large resection specimens. And again, it is due to autolysis, either in situ or on the bench. The scientist here is puzzling about whether or not this, in fact, is going to be okay. But the pathologist is pretty enthusiastic because even though the normal glands here are staining very weakly, the tumour's staining positively, and there are some positive stains in the background. So this is interpretable by the pathologist. Here we have another stain where the scientist is looking unhappy. You can see that about 20% of the cells are showing moderate to weak staining, probably due to autolysis. But the pathologist is actually okay because there's enough staining here to say that there is real staining in the tumour. So top tip number 2 is, even though it looks terrible, it might still be okay. In an autolytic specimen, I will accept the staining as okay if more than 10% of the tumour cells show moderate staining. Is this okay? Yes, this is okay. What's happening here? What we have is a tumour that has formed a subclone. And this is the tumour here. And it was growing fine with its mismatch repair intact. And then it has had a mutation and its mismatch repair has been broken. So I know that this is not a germline mutation because at least some of the tumour has shown that it can stain normally. So top tip number 3, sometimes heterogeneous staining is not due to autolysis, it's due to tumour subclones that have acquired a mismatch repair deficiency. And you can interpret these as not germline mutations, i.e. not Lynch syndrome. Note that the internal control here is still positive, which also confirms that it's not autolysis. What if just one stain fails? Perhaps the bad stain fairy flew past. We often don't know why one stain fails, and it can happen in any specimen. So here we have the technical staff member who is looking a bit unhappy. But the pathologist is going, well, actually, that's okay because the technical failure happened in MLH1 and PMS2 is still normal. We know that PMS2 must be lost if MLH1 is lost. So if we see PMS2 as being positive, we know that MLH1 is really okay and it must be a technical failure. This is still interpretable. So if the big sisters, MLH1 or MSH2, fails and the little sisters, PMS2 and MSH6, are intact, then there has been a technical failure that caused the staining loss, as MLH1 and MSH2 are never lost alone, and the pathologist can still interpret it. Therefore, can we just use PMS2 and MSH6? In an ideal world with well-preserved tissue, yes, to save money. If there is poorly preserved tissue, all 4 are needed to back up the interpretation. The 2-stain method fails to detect some patients with Lynch syndrome because significant weaker staining than the control may be incorrectly interpreted as MSH6. I'm going to show you this in a minute. And weak or focal patchy MSH6 can be retained with the absence of MSH2. So here we have case 1, where we have very much weaker staining in MSH6 and intact control staining in the stroma. Is this positive or is this negative? There is considerable loss. So I would interpret this as loss of MSH6. And if the MSH2, the big sister, was also lost, then I would know my interpretation was confirmed. All right. Top tip number 6. Sometimes there is cytoplasmic staining in DNA mismatch repair. Sometimes it is faint, suggesting a background blush, and sometimes it is quite heavy. Staining in the cytoplasm indicates a mutated protein product and is not a technical failure. If the nuclei are negative, and it's easily seen here, then this stain shows DNA mismatch repair deficiency. Here we can see through the dark staining that the nuclei are negative. So this too is also readable as DNA mismatch repair deficient. Let's move on to quiz time and see what you remember. This staining in MLH1 is interpreted as deficient. That's right. This is the dotty staining that occurs with the M1 clone and is abnormal. MLH1 has either been switched off by a methylated promoter or there is a mutation in MLH1. The pathologist says that the stain hasn't worked. What should you advise? You should advise that they try very hard to find the curettings, even if they're at a different lab, and interpret them. The stain's fine. We can see that here, where there's been better blood supply, there is nice control staining, but it's likely that this has probably been ischemic in situ, and it's lost both the background and the tumor staining, and there is nothing you can do to make this specimen stain better. How about this one? You notice that BRAF has been requested on an ovarian malignancy. You know that BRAF is only useful in colorectal carcinoma. So what is the correct response? Should you do the BRAF? Should you talk to the pathologist, as methylation testing is much more appropriate for gynae cancers, or should you read the pathology report? The answer is that you should read the pathology report. Ovarian cancers can either be endometrial cancers, in which case methylation testing would be more appropriate, or they could be a metastasis from the colon, in which case BRAF would be more appropriate. Your pathologist might not know about methylation testing on endometrioid tumors, and so you look at the pathology report. If it says it's metastatic colorectal carcinoma, go ahead and do the BRAF. If it says it's either primary or secondary endometrioid adenocarcinoma, then please talk to the pathologist about methylation staining. Thank you, everybody, as we finish this recording. I hope that you now know a little bit more about DNA mismatch repair. Kia ora.